Hello, calculus students. I want to share 3 problems with you, each which will serve, I think, as a good review for the exam. We will see a common theme in a couple of these problems. The first one is a solid of revolution. We're going to rotate this region R around the line y equals -2, and we're going to use the washer method. So you can see the little element rectangle right here. We're going to rotate around y equals 2. I'm going to pause the video for a second, and I want you to stop and think about what the inner radius is and the outer radius for this washer. Okay, so the answer to this question, the inner radius, which I'll highlight here in this orange, is going to go from the bottom of the region to here. So that's my little inner radius, and I'll call that R. And R, I will find by subtracting the current, this x-axis has the line y equals 0, to y equals -2. To find the distance, I will subtract the higher value minus the lower value. And 0 minus a -2 is 2, which makes perfect sense. That distance should be 2 because the line y equals -2 is 2 units below the x-axis. The second question was about the larger radius. We'll call that capital R. And let's use a different color here. And that one will go from a fixed element, it'll come down to here. I'll call that capital R. This is different than the region R, which we talked about before as naming the region. Okay, so this R, again, we just subtract the y values. The y value up here is f of x, and so we have f of x as the upper y value, and we subtract the lower y value. So we get f of x plus 2. Makes perfect sense because the top is at f of x above the x-axis, and the bottom one is 2 units below the x-axis. You just subtract the 2. Those are the 2 radii that you would use in your formula when you find the volume by the washer method. Okay, that's all for that problem. We will see something similar to it in the next one, which is one of the homework problems. I don't even remember which number it was now. But this is the side view of a tank. There's a tank behind this. This is just looking at it face on, pumping water out to a height that's 7 units above the tank. I think it was 3 feet to the ground and then 4 feet above the ground, or maybe vice versa. Okay, so I want to talk about how far does the slab get pumped. That's really ultimately what we're looking at. And one thing I don't think we've done a great job at on our homework is really specifying our coordinatization. And by that, I mean the number line, so to speak, that we use to describe our variable in question. Here is y. So y equals 0 anchors this, and the reason we need to have y equals 0 at the center, as opposed to maybe y equals 0 at ground level or at the bottom of the circle, I mean, those all would be possible. But the reason we need it to be at the center the way we have it set up here is because we've used this equation x squared plus y squared equals 2.5 squared. That equation implicitly states that the origin is at the center of the circle. So y equals 0 is, so to speak, the height, but it also relates to that equation. And that forces the center to be here with a y coordinate of 0, and it tells us what the y values are for every single point in this figure. Okay, the very top figure, the reason that's 9.5 at the very top is because the top of the circle is 2.5 feet. Then we go another 3 and another 4 makes 7. The very bottom of the circle is going to have a y value of -2.5. Okay, an arbitrary slab like I draw on right here is simply going to have a y as its value. So I have a y sub k here, meaning it's like our kth slab. But I could also have a slab down here, and its value would be y. It would be a negative y value. That's okay. In absolute values, the distance would be the vertical distance to the center. Okay, so that's the setup. Here's the question, and I'll give you a second to think about it. What distance will any given slab, whose we've labeled as y sub k, be pumped to exit the top of the tube? So think about that for a second. Okay, this is just like the previous problem, where to find the distance, there it was a radius, but here it's a distance pumped. We just need to know our two values and we subtract them. So the y-coordinate here is y sub k. The y-coordinate here is 9.5. Okay, so y equals and y equals. Those are the two y values, 9.5 and y sub k. So if we want to know this distance between them, you just subtract your y values. So the answer should be distance equals 9.5 is the top value minus y sub k, which is the lower value. Now, there's a lot more that goes on in this problem. In particular, you're going to have to find the distance of that across of that slab, which would be 2x, because this point right here is the point xy. So this distance from here, from the center over, is x, all across is 2x, and then you would multiply the length of that, the width of that slab by the length of the tank, which I think was 12, if I remember. I forget exactly what that was. Then you multiply by the delta y, all of that to try to find the area of the slab. But I was just focusing here on the distance that the slab gets pumped. And the importance of labeling where 0 is, labeling what y denotes in your figure. And here, y was the coordinate on the number line that ran through the center of the tank face. Okay, so that made it similar to the last problem where we found the distance or radius to be, again, subtracting two y values. Okay, so now we go to the very last problem. This was the chain problem. And we have this crane, so to speak. It's going up and it's got this chain that is 40 feet long. And the question was, how much work is done in pulling up 15 feet of the 40-foot long chain? And when you pull up that 15 feet, of course, the ball comes with it. The chain weighs 2 pounds per linear foot, and the ball weighed 50 pounds. Okay, I previously did write this solution out somewhere, but I think I need to explain more about it, because I didn't really like the answers that students gave. Well, I should say I don't think they were explained well. Okay. If you pull up 15 feet here, what you can notice is that the very bottom 25 feet and the ball, that's right here, they all just move up 15 feet. So the bottom 25 feet and those 25 feet weigh 2 pounds per foot, so 2 times 25 equals 50 pounds. And the ball weighs 50 pounds. So the total of the weight of that bottom 25 feet and the ball is 100 pounds. And together they move exactly, all of that whole section, this part of the chain and the ball, you can treat it as one entity. They move 15 feet, which means that the work done to do that is force times distance. And the force, we said, weighs 100 pounds, and the distance is 15 feet. And so that is 150 pounds. Okay, actually I made a mistake there. That's 1,500 pounds, of course. 100 times 15. So is that all we had to calculate? No, we have not at all calculated the work needed to move the top 15 feet. Okay, we've only moved the bottom part. And the top part is different because that top 15 feet, as we start pulling it in, some of it starts, it's not moving anymore, right? Like a certain part comes there, it's not being pulled up, it's laying on the side, or it's kind of already reached its height. So there's some mechanism here that wraps up the chain. But we're not having to pull that anymore. As we pull up that ball, it gets lighter and lighter because there's less chain out there. Okay, again, that bottom 25 feet and the ball together that just moves 15 feet. We can just not even use calculus, just multiply the force times the distance. But the top 15 feet, we need to use some calculus, and that would be 15 feet. Let me just draw this part here, 15 feet. And let's, so there was this other part and it had the ball on it. But now we're just focusing up here. And let's just partition it up, pick a little piece here of length delta y, and we'll figure out how much work is done in pulling up that one little piece. Okay, so here's the top at y equals 0. Here's the bottom at y equals 15, and we're going to break it up into pieces. And the work, we'll call it delta w, to move one piece of length delta y is the weight of the piece times its distance. Okay, and the weight of the piece is going to be 2 delta y because it weighs 2 pounds per linear foot, and the length is delta y feet. So that's the force, and the distance is simply going to be y. Why is that? Well, y equals 0 is at the top, and we have height y here. You could call y sub k if you want. And so that distance between them is y. So y varies from 0 to 15. Okay, 2y delta y. And the total work to move it, then we're going to integrate to move those 15 feet of chain. We're going to integrate from 0 to 15 of 2y delta y, dy, which is y squared from 0 to 15, and you get 225 foot-pounds. Okay, so altogether, the total work, we take our two pieces, and we had 1,500 plus 225 is 1,725 foot-pounds. And the solutions that students gave, many of you did it all in one shot, and you just did one integral, and student work usually use one integral. And some integrated from 25 to 40. And I don't think you explained real well how you chose those bounds, and you didn't explain what the y represented. And then you had some dy here. So if you want to re-explain that to me somehow, I think that's what I need in order to give you full credit for this. You can get the right answer by just integrating from one bound to another. But in particular, you need to explain what the distance is. Here it was real clear with my distance on the top 15 because I was actually moving that section, and every part from 0 to 15 got moved. But the whole chain is moving here, all the way from 0 to 40. So when you only integrated over part of it and didn't explain what the distance was, I think that was insufficient. I kind of gave an explanation in my solution, which is one way to see it, different than the one I gave here. But nobody quite did it that way either. So think about your integral and what your distance denotes and what it actually is that you're chopping up, okay? Are you chopping up what's being pulled? Are you chopping up what's moving? Make it real clear what your little delta y denotes for this problem. All right, that's it. 15 minutes was long enough. Thanks.